Well, in the last lecture, we had defined the dual space and the linear functionals, and we had also stated some examples for evaluating the dual basis of a dual space with respect to a given basis of the vector space. Now, in today's lecture, we will define the transpose of a linear operator and then discuss some results about how we construct its matrix and the other related properties. So let us state this theorem, and within the theorem, we will define what is transpose of a linear operator. A theorem. Let T be a linear operator on V. That is, T is an element of LVV. Define a mapping. Define a mapping T star from V star into V star by the rule the rule is T star f of some vector x. This is equal to f of t of x, where x belongs to V, and for all f belonging to f. For all f belonging to the dual space V star. Then this linear transform, then this mapping T star, this belongs to L V star V star. So therefore we are defining a mapping T star from dual space to itself by the rule T star f of x is equal to f of t of x for all x belonging to V and for all f belonging to the dual. Then we are actually going to prove that this T star is a linear operator on V star. Now, before doing the proof, we shall look for how this mapping works. Now here we have T is a linear operator on V. So therefore, T of x is an element of V. Where x is an element of V, then T of x is also an element of V. Now f is a linear functional on f is a linear functional, so f is a mapping on V to f, and therefore this f T of x is well defined. Now again, this x is an element from V, and f is a mapping on V, which is a linear functional. So this f of x is an element of, it is actually a scalar in the scalar field over which this V is a vector space. And so this T star f of x is also well defined, and this f T of x is also well defined because this T of x is in V and this x is in V. So this is how this linear transformation works on the vectors in V, and the images of those vectors under the linear transformation T, which is defined from V into V. Now let's do the proof. First of all, we show that this T star f is a linear function. First, we show this T star of f is a linear function. And for this thing, let suppose alpha, or let's first choose this V1, V2 belonging to V. Then this T star f of v1 plus v2. Now by definition, this is equal to f of t of v1 plus v2. And this comes from the definition of this t star of f of x, which is defined to be equal to f of t of x. So therefore, this t star f v1 plus v2 is equal to f of t of v1 plus v2. But now here we can use the fact that this t is a linear map and f is also a linear map. So therefore, this can also be written as this is f of t of v1 plus t of v2. So therefore, T is a linear map. We have used that definition. But now here we can use the definition of F being linear. So we can write this as F of T of V1, then plus F of T of V2. But now, again, by using this definition, T star F of X is equal to Ft of X. So here we have Ft of V1. So this can be written as this actually T star F of V1. Then plus T star F of V2. So therefore, we have shown that this T star F is linear over the vectors. Now again, and this is true for all. This is for all V1, V2 belonging to V and F belonging to V star. Now again we have this thing T star F of alpha times V. Now again by definition this is equal to F of T of alpha V. But now here we can use the fact that T is a linear map. So this is F of alpha T of V. Now F is a linear map, so we can take this alpha common outside. So this alpha times F of T of V. But now again using the definition of F of T of V, that is equal to alpha times T star of F of V. So therefore, T is linear over the scalar multiplication. So thus we have shown that thus this T star F is a linear function. And finally, now we will show that this T star is a linear map. Now finally, we show T star is linear. And for this thing, what we have for F1, F2 belonging to V star, we have this T star of F1 plus F2 of V. Now this is by definition equal to F1 plus F2 of T of V. And this is from the definition how we have defined the mapping T star of F. But now this can be written as, now since this F1 plus F2 is linear, so this is F1 of T of V plus F2 of T of V. But now by definition, this first one is equal to T star of F1. This is T star F1 of V, and the second one is T star F2 of V. So thus we have shown that thus T star F1 plus F2, this is equal to T star of F1 plus T star of F2. So therefore, this T star is linear over the vectors. Now again, this T star of alpha f of v. Now T star alpha f of v, again by definition. Now since alpha f is a linear functional, so this is alpha f times alpha f of T star of v. So this alpha f of T star of v. But now, since f is a linear map, so we can write this as f of alpha T star of T of v. So actually, we have, this is not T star here. So this alpha T of v. Now, since T is linear, we can use that function property here. So this is T of alpha of v. But now, by definition of the linear operator T star, because we have defined T star of f is equal to ft of alpha. So now this is equal to T star of f of alpha v. So this is equal to T star f of alpha v. But we have already seen that this T star f is a linear map. So we can use that thing here. So this is equal to alpha times T star f of v. So therefore we have shown that thus T star alpha f, this is equal to alpha T star of f. So therefore we have completed showing that this T star is a linear map. So thus this T star belongs to the set of linear maps from V star into V star. Now let's take up a definition. The mapping, the linear map T star from V star into V star defined by T star of f of x is equal to f of t of x, which we have shown in the previous result that this is a linear function. Now this mapping is known as, is called the transpose of, this is called the transpose of linear operator T. This is most of the time is denoted by T star, and this is also denoted by T transpose. This is also denoted by T transpose, read as the transpose of T. Read as transpose of T. So once we have defined the transpose of a linear operator, now we will look for how the matrix of this transpose T star looks like. So that is
3 o'clock.
contained in this theorem. Let T be a linear operator on V, and let V1, V2, Vn be the basis. Be the basis of V, and F1, F2, Fn, and F1 through Fn be the basis of V star, be the basis of V star dual to the basis V1, V2, Vn. So in fact, wire. So that is this Fi of Vj is equal to delta Ig. So here this V1, V2, Vn is a base of V, and then its corresponding dual basis for V star is F1, F2, Fn, and we know that this Fi of Vj is defined to be equal to delta Ij, where this delta Ij is already defined in the previous lectures to be the Kronecker delta function. Then the matrix of T transpose. Then the matrix of T star with respect to the basis F1, F2, Fn is the transpose of matrix of T with respect to the basis V1, V2, Vn. So therefore, this theorem states that if we have a basis V of a vector space V, and then the dual basis of V star corresponding to this basis, then the matrix of T and the matrix of T transpose are related by a relation that matrix of T transpose is just the transpose of the matrix of T, and why this transpose is just the matrix transpose. So now let's do the proof. So given that, now let's name it beta equal to V1 through Vn is the basis of V. Is the basis of V, and beta star equal to F1 through Fn is the dual basis of V star, is the basis of V star dual to beta. Again, let A and B be the matrices of T and T star respectively. So let's call the matrix of T as A and the matrix of T star as B. Now first we will try to construct the matrix A, and then we will show that A transpose is equal to B. Now we have T of Vi is equal to summation j from 1 to n alpha ji into Vj. So this equation we are able to write because we know that T is a linear operator from V into V, and this V1, V2, Vn is a basis of V. So therefore, every T of Vi can be expressed as a linear combination of the vectors Vi's from the basis beta. We have this because this T is a linear operator from V into V, and this V1 through Vn is the basis of V. And in fact, here this I runs from 1 to n. So therefore, j runs from 1 to n, and in fact, it's I runs from 1 to n. So that is what we have. Now again, suppose now, therefore, we have completed. So therefore, what is this matrix A now? So thus, this matrix A. Now the first column of this matrix A is the coordinate vector of T of V1 related to the basis beta. Now T of V1 will be summation j from 1 to n alpha j1 Vj. So the first column of this matrix will be like alpha 1 1, then the second entry will be alpha 2 1, and then alpha 3 1, and so on, alpha n 1. So this will be the first column of the matrix A. Then the second column will similarly be T of V2. So it is summation j running from 1 to n alpha j2 Vj. So it is alpha 1 2, then alpha 2 2, and so on, alpha n2, and so on. Now here this will be alpha 1n, alpha 2n, and this is alpha nn. So therefore the matrix A is alpha ij n cross n. Now we will try to look for the matrix B. Now suppose this T star of Fi, this is equal to summation j from 1 to n beta ji Fi, where this F1 through Fn is the dual basis of V star. Is the dual basis of V star. With respect to the basis, V1, V2, Vn of V. So then what we have to show, we just have to show that beta ji is equal to alpha ij. Then we have to show that beta ji is equal to alpha ij for all I and j. For all 1 less or equal to I and j, and less or equal to n. Now let's see what we obtain from this equation. Now we will evaluate this T star Fi of Vk, where Vk is some element from the ordered basis beta of V. Now this by definition is equal to summation j from 1 to n beta ji Fi of Vk. So we have this equation. Now we will look for what is the left-hand side of this equation and what is the right-hand side of this equation, because the coefficients here are the coordinate vectors and they actually form the columns of the matrix of T star, which we have denoted by B. So now the left-hand side is this T star the left side is T star Fi of Vk. Now by definition of the mapping T star with the transpose linear operator, and this is defined as Fi of T of Vk. But now by definition this T of Vk is an element of V and beta is a basis. So this T of Vk can be expressed in this way. So therefore we have this T of Vk is equal to summation j from 1 to n alpha jk Vg. So therefore here we have this is equal to Fi of. Now T of Vk, it can be written as summation j from 1 to n alpha jk Vg. But now this Fi is a linear operator. So we can write this is equal to summation j running from 1 to n. This is alpha jk, then Fi of Vg. But now this is equal to, this is now j running from 1 to n. So the first term is alpha 1k Fi of V1. Then the second term is alpha 2k Fi of V2. And similarly, the ith term is alpha ik Fi of Vi. And the last term in this sum is alpha nk Fi of Fn of Vi. But now by definition of these linear functionals Fi, we have defined them to be the mappings which satisfy Fi of Vg, and they are defined in this way. This is equal to delta Ig. So therefore, whenever I and j are different, this mapping is equal to 0. The image of Vg is 0. And whenever I and j are identical, when they are same, we get Fi of Vi is equal to 1. So therefore, the first term in the sum is equal to 0. The second term in the sum is equal to 0. And every term in the sum is equal to 0 except the I, possibly the ith term. So therefore, what we obtain here is that this sum is just equal to alpha ik Fi of Vi, because all the remaining Fi of Vg are equal to 0. But now Fi of Vi is equal to 1, so therefore this is equal to alpha ik. So therefore the left hand side of this equation is, let's call this as equation number 1. The left hand side is just alpha ik. Now let's look for the right hand side. Now again, right side of first is, and that is summation, the right hand side is summation j from 1 to n beta ji fj of vk. Now immediately substituting the different values of j from 1 to n. The first term here is beta 1i f1 of vk. The second term is for j equal to 2, that is beta 2i f2 of vk, then plus so on. Then the kth term is beta ki f k of vk, and then similarly the last term is beta ni f n of vk. Now again, using the definition of these linear functionals to be defined by this fi of vg. Now again, this is equal to delta ig. So therefore, using this thing here, now this first term, alpha 1 of vk, this is 0, alpha 2 of vk is 0, and similarly, this f1 of vk is 0, f2 of vk is 0, and fn of vk is 0, and this fk of vk is equal to 1. So therefore here we obtained this first term is 0, second term is 0. Actually every term is 0 except this possibility, this bki fk of vk. So therefore the only thing that we get here is bki fk of vk. Now again by this definition, this fk of vk is equal to 1. So this is just equal to bki. So thus the left hand side of, thus we have from first, since we have shown that the left hand side is equal to alpha ik and the right hand side is beta ki. So therefore we have alpha ik is equal to beta ki. And this is true for all I and k. For all I and k. But now this alpha ik, it is the ik entry of the matrix A, and beta ki, this is the ki entry of matrix B. So thus matrix of this T star is the transpose of matrix of T. So we have proven that the matrix of T star, which is B, it is actually equal to A transpose. So that is B is equal to A transpose. So this completes the proof. Thank you so much.